This is the second part of our discussion on analytic functions. In our previous discussion, we defined what are analytic functions. We also saw some very simple examples whether those functions are analytic or not. Now in this part, we are going to see some properties which help us in determining whether a given function is analytic or not. Okay? So these kind of conditions are going to be useful when we are doing some calculations and we want to see that a given function is analytic or not. So let's begin with our discussion. Now let's recall ourselves what is an analytic function. So a function is analytic at a point z0 if there exists some epsilon neighborhood of this point z0 such that this function has derivative at each and every point in that epsilon neighborhood. So we say that the function is analytic at this point z0 if there exists some epsilon neighborhood for some epsilon greater than 0. So there exists this epsilon neighborhood and the function is differentiable at each and every point inside this neighborhood. Okay, so if we choose any point inside this neighborhood, then it will be differentiable at that point. Okay, so in other words, f must be differentiable not only at z0 but also at all points in some epsilon neighborhood of z0. Now, what are the necessary conditions? So we know that if a function is differentiable at a point, then it is continuous at that point. So the necessary condition for a function to be analytic at a point is that it must be continuous. Okay, and if we go further, then if function is analytic at a point z0, then it must be continuous in some epsilon neighborhood, because it must be differentiable in some epsilon neighborhood. So if it is differentiable at each and every point in that epsilon neighborhood, then it must also be continuous in that epsilon neighborhood. So we can say that if a function is continuous in some epsilon neighborhood of z0, then the necessary condition is satisfied. And of course, it is not the sufficient condition. Okay, so it is just a necessary condition. So for example, if we have a function which is not continuous in any epsilon neighborhood of z0, so we can say that it is not analytic. Okay, so it's a very useful property if we have a function which is not continuous at any point, okay, in any neighborhood of z0. Okay, so that's how we use necessary condition. Now another necessary condition is satisfaction of Cauchy-Riemann equations, and once again it's a necessary condition, not the sufficient condition. Okay, so in other words, if this condition is satisfied, if a function is satisfying CR equations or Cauchy-Riemann equations in some epsilon neighborhood, then this does not imply that the function is analytic. But this gives us once again another supporting argument. Okay, so for example, if we know that a function does not satisfy Cauchy-Riemann equations in any neighborhood, okay, so if we take any neighborhood of z0, then every neighborhood of z0 contains some points where Cauchy-Riemann equations are not satisfied, then we can say that the function is not analytic. Okay, so precisely consider this point z0, and whenever we consider an epsilon neighborhood, if we can find a point, for example, where Cauchy-Riemann equations are not satisfied, okay, so CR equations not satisfied. Similarly, if we consider another neighborhood, okay, so and in this neighborhood, if we can still find another point where Cauchy-Riemann equations are not satisfied, and moving on, okay, so whenever we consider an epsilon neighborhood, we can find a point where Cauchy-Riemann equations are not satisfied, then we say that the function cannot be analytic at point z0, because Cauchy-Riemann equations are the necessary condition for differentiability. Okay, so if Cauchy-Riemann equations are not satisfied for example at this point z prime, then this function will not be differentiable at z prime, and so in this neighborhood the function will not be differentiable. Okay, so that's how we use these necessary conditions for checking the analytic behavior of a function. Now the next question is, so far we have seen two necessary conditions for a function to be analytic at a point. It must be continuous at that point, and it must satisfy CR equations. Okay, so of course these are the necessary condition for the differentiability of a function. Now the question is, can we find some sufficient conditions? Okay, so conditions, when a function satisfies those conditions, then the function becomes analytic at that point. Now this is our next topic, to find conditions when f is analytic at a point. Now there is a very simple answer to this thing. The differentiation formulas. Differentiation formulas help us in finding analytic functions. So how do they help us? Now the idea is very simple. If f and g are two analytic functions, then f plus g is also an analytic function in the same domain D. Okay, so what is the reason behind it? We know that if f is differentiable and g is differentiable, then their sum is also differentiable. Okay, so for example, if we are given a point z0 and the function f is analytic at z0, so in other words there exists some neighborhood, epsilon neighborhood of this point z0 where f is differentiable. The derivative of f exists at each and every point in this epsilon neighborhood. And okay, so f is analytic at z0. Okay, so this is the consequence of this. There exists an epsilon neighborhood and function is differentiable at each and every point in this epsilon neighborhood. Now if g is also differentiable, if g is also analytic at z0, okay, so it means there exists some other neighborhood. So now let's call this epsilon 1 neighborhood. Okay, so g is analytic at z0. Okay, now we can say that there exists some neighborhood where f and g both are differentiable. Okay, so in this case, since we are taking this epsilon 1 to be less than epsilon to be less than epsilon 1, so that's why we can say that in this neighborhood, okay, so in this shaded neighborhood, f and g both are differentiable. Okay, so we can say that f and g both are differentiable in this epsilon neighborhood. So, and we also know that if f and g are differentiable, then f plus g is also differentiable. So this is the property that we discussed when we were discussing the differentiability of complex valued function. So f plus g is differentiable in the same region. So this implies that f plus g is analytic at point z0. Okay. Now similarly, if we have a difference of the functions f minus g, then the same argument holds. And if we have product of two functions, then the same argument will show that the product is also analytic. So in other words, if f is analytic at point z0 and g is analytic at point z0, then their product is analytic at the same point z0. Okay, so in general, if f and g are analytic in a domain D, then f into g is also analytic in that domain D. Okay. Now what about the quotient? The quotient, since we know that we are not allowed to divide by 0, so that's why we have an extra condition. If f is analytic at a point and g is analytic at a point, then f over g is analytic if the denominator is not 0 at that point. So in other words, this f over g is analytic in a domain D provided the function in the denominator does not vanish at any point of D. Okay, so this is the condition that we have to impose. Okay, so the consequence of these simple properties are very important. So for example, if we are given two functions, okay, so let's call it f of z, which is given to be z cube plus z plus 1. Okay, so this is one function, and if we are given another function, let's say g of z, let's call it okay, so z is to power 4 plus z minus 1 or plus 1. Okay, so just two random polynomials, because so far we have seen that a polynomial is always differentiable, and so polynomials are entire functions as well. Okay, so this implies that f plus g, which is a new function, is entire function. Okay, so since we know that this f of z is entire function being a polynomial, and this function g of z is also an entire function being a polynomial. And similarly, we can add other functions. So since we have only seen polynomials so far, which are analytic, and some other functions, so for example 1 over z. Okay, so we can consider another example where we take one function to be, for example, a polynomial. Let's say f1 of z to be 1 over z, and let's take another function g of z, g1 of z to be, let's say, z cube plus 1. Okay, now we want to see that if this function is, okay, so we want to see if f plus g is analytic at, for example, z is equal to 1 plus iota 1. Okay, so 1 over z is analytic at this point, and g1 of z is analytic at this point as well, because this is a polynomial, and polynomials are always differentiable and hence analytic at each and every point. In fact, they are entire functions. So that's why this f plus g is analytic at this point. Okay, so as I told you earlier, we have seen a very limited number of functions which are analytic. But as we will move on with our discussion, we will find many other functions that we will prove using some other methods that these are analytic. Then these simple properties will help us to build new functions which are analytic. So for example, adding them and then subtracting them and dividing them as well. Now let's consider a little bit more complicated example, where we have a rational function. In other words, it's a polynomial over a polynomial, and we want to see at what points this quotient of two polynomial or rational function is analytic. Okay, so we have seen that polynomials are entire, so let's call the numerator to be f of z is equal to z raised to power 4 plus 1 is entire function. In other words, it is analytic at each and every point in the complex plane. Okay, now what about the denominator? Let's call it f2 of z. So once again, this is a polynomial. Okay, so multiplication of polynomial is a polynomial. So z square plus 1 multiplied by z minus 3. So this is once again an entire function, is an entire function. What about the quotient? Now we have seen that the quotient is analytic apart from the points where this denominator is 0. So where the denominator is 0, so we need to find the points where z square plus 1 and z minus 3 is equal to 0. So this is 0 at points where z square plus 1 is 0, or we have z minus 3 equal to 0. So in other words, we have points z is equal to plus minus iota, or z is equal to 3. So apart from the points plus minus iota and 3, the function, the given function, which is the rational function f of z, is analytic. Okay, so that's how we use this simple properties to find whether a given function is analytic or not. Now similarly, we have also seen that if we are given a composition of function, and if both functions are differentiable, then their composition is also differentiable. So when we will apply in this analytic function case, then the consequences are once again very important. If we are given two functions f and g, and both functions are analytic, then their composition is also analytic, and in fact we can also calculate the derivative using this formula. Okay, so this is not in the power, it's basically like this. Okay, so and of course the simple conditions that whenever we apply f on the domain D, then f of D must be contained in E. Okay, so otherwise we cannot apply G on that output of f. Now, if a function is given in the component form u of xy plus iota v of xy, then we can apply Cauchy-Riemann criteria for differentiability to check whether f is analytic or not. Now remember, we have a sufficient condition for checking whether a function is differentiable at a point or not. So if we want to check that a function is analytic at a point, we can check that whether there exists a epsilon neighborhood where the function has derivative at each and every point in that neighborhood, and we can check that using this sufficient condition, which is the Cauchy-Riemann criteria for differentiability. Now let's have a look at what is this criteria. So in this criteria, if a function is defined in some neighborhood of the point, so this is the point where we want to check the differentiability. If all the partial derivatives ux, vy, uy, vx exist everywhere in the neighborhood, okay, so the second condition, okay, so the first condition is it must be defined in the neighborhood. The second condition is the partial derivative must exist everywhere in the neighborhood, and the third condition is the Cauchy-Riemann equations are satisfied. Okay, so the partial derivatives are continuous and Cauchy-Riemann equations are satisfied. So if these conditions are satisfied, then the function is differentiable. Okay, and of course we can also find the derivative using the formula that f prime z naught is equal to ux x naught y naught plus iota vx x naught y naught. In other words, just take the derivatives of the component function with respect to x, or if we want to take the derivatives with respect to y, then you need to add a minus sign when we are taking derivative, and of course the order is also changed. So it's vy x naught y naught minus iota uy x naught y naught. But it's simple to use just this criteria. Now let's consider this function f of z, which is equal to cosine hyperbolic x cosine y plus iota sine hyperbolic x sine y, and of course this is in fact f of x plus iota y. Now we want to find the points of the complex plane where this function is analytic. Okay. Now let's consider a very random point in the complex plane known as z naught, which is equal to x naught plus iota y naught, and we want to check whether f is analytic at this point or not. Okay. So the function is defined in the entire complex plane, so that's why it is defined in some neighborhood of z naught. So this condition is satisfied. Now let's go to the next condition, if all the partial derivatives exist everywhere in the neighborhood or not. So in this case we can find what is ux, what is uy, what is vx, and what is vy. So we can easily find this thing using the formulas for the partial derivatives, and these derivatives exist in the whole complex plane, so that's why they exist in every neighborhood of the point z naught. Now moving on to our next condition. So the partial derivatives must be continuous and they satisfy the Cauchy-Riemann equation. Now what is ux in this case? Sine hyperbolic x cosine y, and what is vy in this case? Sine hyperbolic x cosine y, and the first Cauchy-Riemann equation is satisfied. Now let's see whether the second condition is satisfied or not. So uy in this case is minus cosine hyperbolic x sine y, and what is vx in this case? So vx in our case is basically cosine hyperbolic x and sine y, and we can easily see that the second Cauchy-Riemann equation is also satisfied because uy is equal to minus vx. Okay, so then we can say that the function f is differentiable, but since these conditions are satisfied at each and every point in the complex plane, so we can say that the function is differentiable at each and every point in the complex plane, and hence it is analytic at each and every point in the complex plane, because it is differentiable at each and every point in the complex plane. Now, there are also some other results that can be used to check whether a function is analytic at a point or not. So, for example, the polar version of these CR conditions. Okay, so we have discussed this when we were discussing the Cauchy-Riemann equations and their polar version. So, we can also use these conditions to check the differentiability in some neighborhood of a point. So, in this discussion, we have seen some criteria that can be used to check whether a function is analytic at a point or not. In our further discussion, we will see some consequences of this condition of analytic functions.